Hello! We are switching to a new topic today. So far, we have been talking about strategic games, where individuals choose strategies that benefit themselves the most. But there are games where groups of players can work together to obtain higher utility, and these are the cooperative games. We will start with an example. Suppose Alice, Bob, and Carol want to buy ice cream. There are three possible sizes of ice cream: 1 liter, 1.5 liters, and 2 liters. And they cost $7, $9, and $11 respectively. Now Alice has $3, Bob has $4, and Carol has $5. On their own, they cannot buy any of these ice cream. But if they pool money together, they can get some ice cream. For example, if Bob and Carol put their money together, they will have $9. Then they can buy a 1.5 liter ice cream. So this is an example of a cooperative game, where utilities could increase if players form coalitions. We now give some definitions. A cooperative game is given by a set of players N and a characteristic function v that assigns a value v of s to each coalition S of players. We use NV to represent this game, and the set N by itself is called the Grand Coalition. In our example of the ice cream game, the set of players N is A, B, and C, and the characteristic function v can be defined using this table. For the empty set and any subset of size 1, the value is 0. They cannot buy any ice cream. If Alice and Bob form a coalition, then they have $7 to buy 1 liter of ice cream. Alice and Carol together can buy 1 liter. Bob and Carol together can buy 1.5 liters. If all three of them combine to form the Grand Coalition, then they would have $12, enough to buy 2 liters of ice cream. And this is how we define a cooperative game. A couple of general assumptions that we will make about the characteristic function. We will assume that the empty set has value 0, and for any coalition S, the value is non-negative. Here are 2 more examples of cooperative games. Suppose we have a country that has a 101-member parliament. There are 4 parties, A, B, C, and D, and they have 40, 22, 30, and 9 members respectively. Now they need to decide how to spend a $1 billion windfall. To do that, they need to form a majority to spend it. So in this case, the set of players is A, B, C, and D, and the characteristic function is v of s, which is 10 to the 9 if the parties in S have at least 51 members. It will be 0 otherwise. Our third example is more combinatorial. In the matching game, we are given the graph G and edge weights W. The players are the vertices, so V is equal to N. We can think of the weight of an edge as representing the benefits if the 2 vertex players work together. Here is an example of a graph with edge weights. For any subset S of the players N, which are the vertices, its value is the maximum weight of a matching using vertices in S. For example, if we take these 4 vertices in the blue set, the maximum weight matching here consists of these 2 edges, so the value of this set is 15. If we consider this purple set here, the maximum matching consists of just the middle edge, so its value is 10. So these are 3 examples of cooperative games. Now you might be wondering, what do we want out of a cooperative game? Recall that the outcomes of strategic games are the strategy profiles, which could be pure strategy profiles or mixed ones. A strategy profile records which strategy is played by each player. In cooperative games, we do not have individual choices here. Instead, we have someone from the outside who decides what should the players do and the benefits that they will receive. So there are two parts to an outcome of a cooperative game. The first part is we divide the players into groups, which we call coalitions. This is a coalition structure. Now each coalition will generate their assigned value, which we get from the characteristic function v. So the second part of the outcome is that we distribute the value that each coalition generates among its members. This is called a payoff vector. We now give some formal definitions. Given a cooperative game and V, a coalition structure is a partition pi of n. This means that pi is a certain tuple C1 to Ck, where each Ci is a subset of the players n, the Ci's are disjoint, and they combine to form the set of all players n. A payoff vector is a vector x in Rn such that x is at least 0, and the sum of xi for each I of a coalition Cj is at most v of Cj for each j. This means that the payoffs received by the members of Cj is at most the value generated by the coalition Cj, which hopefully makes sense. As a notation, for any t that is a subset of n, we write x of t to be the sum over the members I of t, the values xi. So the inequality here can be rewritten as x of Cj is less than or equal to v of Cj. Then, an outcome consists of two things, pi and x, the coalition structure and the payoff vector. Such an outcome is efficient if x of Cj is equal to v of Cj for all j. This means that you distribute all the values generated by Cj to its members. For example, an outcome of the ice cream game is pi x, where pi consists of two coalitions A, B, and C, and for the payoff vector x, xa is 0.5, xb is 0.5, and xc is 0. And this outcome is efficient. That is because the value generated by A and B is 1, and that is precisely xa plus xb. And the value generated by C is 0, and that is equal to xc. We will now look at several special classes of cooperative games that we will consider in this course. The first is the class of monotone games. A monotone game satisfies this simple implication. If S is a subset of T, then V of S is less than or equal to V of T. This generally makes sense as more people produce more value. But this might not be applicable if, for example, someone does not want to work with someone else, so putting them in the same group might reduce the value that the group generates. Our second class of games are the superadditive games. These games satisfy the condition that, for any disjoint sets of players S and T, V of S plus V of T is at most V of S union T. The meaning of this is that forming coalitions is always better in these superadditive games. Note that superadditivity implies monotonicity, but the converse is not true. And because forming larger coalitions give you higher value, we usually only consider the grand coalition, that is, when the coalition structure pi is just n. Note that all three of our examples of cooperative games are superadditive. Our last class of games is the set of convex games. Now, the condition for superadditive games are defined on disjoint subsets of N. In convex games, we consider those subsets that are not necessarily disjoint. So the condition we need here is for any subsets S and T of N, V of S plus V of T is at most V of S union T plus V of S intersect T. This is called the supermodularity inequality. Now, the meaning of this is not that obvious, but we will give an interpretation soon. Note that convexity does imply superadditivity, but once again, the converse is not true. And here is a proposition that could explain the meaning of convex games. A game NV is convex if and only if, for every S and T, where S is a subset of T, a subset of N, and for every player I that is in N minus T, V of T union I minus V of T is at least V of S union I minus V of S. We will leave the proof of this as an exercise. So what does this inequality mean? We see that V of T union I minus V of T is the value that player I adds to the coalition when it joins T, and similar for S. And since we have the condition that S is a subset of T, this inequality means that a player is more useful in larger coalitions. Now, convex games are harder to find, but they do have very nice theoretical properties that we will discuss later. So that is our brief introduction to cooperative games. Now, knowing the possible outcomes is a start. What we still need to figure out is, what kind of outcomes do we want? We will start discussing some ideas of good outcomes in the next lecture.